Hello, students. Today is Friday, August 28th, or Monday, August 31st. Today's agenda is to do graphical analysis, and you'll see that with numbers like the previous video, and you'll see it without numbers, some sketches. So page 19 in your packet, I had asked you to give it a try, and we're going to go over this and then take a look at the sketches. So on this one, I had given you the hint to start with number 3 and 4. And so down here on 3 and 4, it says, what if it's a velocity graph and the object were at position 4 meters at 4 seconds? And so they want us to do two things in this situation. What would be the acceleration and initial position? So using your strategies with velocity time graph, you can read the velocity, you can do the slope and find acceleration, or you can do the area and find the displacement or change in position. And so for number 3, it says acceleration at 3 seconds. So we're going to do the slope, and if we go up to the graph, 3 seconds is actually where the line crosses the x-axis. Now, the y-axis is not labeled because it applies to both sets of questions. And so imagine it's a velocity graph. Well, at 3 seconds, it has a velocity of 0, so it comes to a split-second stop. And the misconception is that, oh, it must have a 0 acceleration at that point as well. But if you look at the slope of the line that goes through this 3 seconds, it does have slope. So it does have acceleration. And so we would do the slope, and you can't do it of only one spot, the acceleration spot. You must have at least 2 points on the line to do slope. So that change in y over change in x now becomes change in velocity over change in time. Now, what 2 points are we going to include? Well, you can include any 2 points on that line, whether it's at 2 seconds or 4 seconds, or you can do 3 to 4. Either way, I'm going to do 3 to 4 just because, you know, I'm involving the 3. Yesterday I did 2 to 4. It's all the same. It should come out the same. And so if we notice, draw a little slope triangle, you've got your rise or your change in velocity of 3, 0 to 3, and then the base, the change in x or your change in time is 1 second. And so I had 3 over 1, and we end up with a positive 3 meters per second squared. Again, you should get the same answer going from 2 to 4 seconds, as long as it's on that line. And then number 4 says, what is the initial position? So initial position is when it's at 0 seconds. So when the timer begins, where is it? They told us that it was at 4 meters at 4 seconds. So what if I call final position 4 seconds? No, 4 meters. And so I can't solve for the initial position based on final position alone. But remember, the area between the best fit line, the data line, and your axes tells you the delta x, the displacement. So if I have 0 seconds and then that one's happening at 4 seconds, I'm going to do the displacement or the area from 0 to 4 seconds. And so going back up to the graph, we've got a couple different segments. Now I'm going to show you a little handy trick that you can use when doing area. And so we see the first one, 0 to 2 seconds, is a rectangle. Base times height, I've got the base of 2 and a height of -3. Include the negative because displacement is a vector. So base times height, we had a base of 2 times a height of -3. And so from 0 to 2 seconds, we've got 6 meters in the negative direction. Now we have 2 to 3 and 3 to 4. But here's something special. Look at 2 to 3. We've got a triangle underneath, a height of -3, a base of 1. And then just after 3 to 4, we have a height, another triangle with a height of +3 and a base of 1. So we could calculate 1/2 base times height twice, but since they are symmetrical, they're going to cancel each other out. And so just to show as a visual, so this cancels this in the graph. So you can get a numerical answer for each, but because they have 1/2 base times height and the heights are positive, negative, they're going to cancel out. And so because of that, your total final answer for a displacement 0 to 4 seconds is equal to the displacement that is traveled 0 to 2 seconds. So I don't have to calculate anymore. My final answer is that -6 meters. Oh wait, that's not my final answer. That's the displacement. Now I need to go back and get the definition of displacement. And so displacement is equal to final position, we said 4 seconds, minus the initial position at 0. And remember, that's what we're trying to isolate. And so do a little math here. We can add initial position to the other side. So we would get x initial minus 6 equals that final position at 4 seconds. Keep isolating initial position. You got to add 6 to both sides. And so here's our final answer. We got to bring in that given position at 4 seconds. And so we would be at 4 meters plus 6 meters. Here's our final answer. 10 meters is where we started. And if we go back to the, and it's a positive, if we go back to the graph, if we start at +10, and then we have negative displacement, 0 to 3, then we're walking in, hold on. Okay, sorry, hit the wrong button. So we start at a positive location, and we have a negative displacement, but remember that 2 to 4 interval is what cancels out. And so we just have that -6, 10 minus 6 is going to equal that 4 meters that was given. Okay, now let's change gears. So I'm going to erase the V on the axis, switch colors here. Now pretend this is an acceleration graph versus time. I'm going to leave the shading because that'll come in handy with acceleration as well. And so the strategies to remember with acceleration graphs, slope is not important to us. I'm going to put nothing. It's nothing for AP Physics 1. If you move on to calculus-based physics next year, it'll mean something then. But area is going to be our friend on an acceleration graph. So now area doesn't equal displacement because you have an acceleration times a time. An acceleration times a time, and be careful here, it's not equal to any velocity. It's not equal to average velocity. It's equal to a change in velocity, which you can break down like we did before, is equal to a final velocity minus initial. And we're going to be using that because in the prompt it says the object has an initial velocity of -3 meters per second. And it says, does the object ever change directions? If so, when? And then we'll find a velocity at the very, very end. And so Here is where a lot of students make the mistake because they get so used to seeing velocity graphs. Does the object ever change direction? They're like, oh yeah, just where it crosses the axis. Zero velocity. Well, now this graph is an acceleration graph. And so you can't read, oh, it's at 3 seconds. That's where it's 0. That's where the acceleration is equal to 0, not the velocity. And so remember, acceleration relates back to some kind of force. And so I want to draw 3 sketches that are occurring in this graph. And so when the timer begins, we are moving. So here's kind of a path for our person. We are moving to the left. Initial velocity is -3 meters per second. And when the timer begins, something pulls us. Again, acceleration is related to the force. Something pulls us to the negative. And so here we have a negative acceleration. Yeah, it's a 3 value. But if your velocity and acceleration are both the same sign, what's the story behind this? We're going to speed up in the negative direction. And that's what happens from 0 to 2 seconds. Now, 2 to 3 seconds, it's the same story, but notice in 2 to 3 seconds, your acceleration is getting smaller and smaller and smaller. I like to think maybe there's a rope tied around this person and they started out pulling consistently, -3, -3, -3. And then maybe at 2 seconds, the rope starts to come out of their hands, slip out of their hands. And so they're still pulling, just not as much. And so actually that's the story of all 3 seconds. The whole time that object or person is speeding up in the negative direction. Not always at the same rate though. All right, so then, and we haven't stopped. Our velocity is getting bigger, bigger, bigger. Now notice I'm not calculating just yet. And then what happens at 3 to 4 seconds? Well, now I'm going to draw another little picture. So maybe we're further on the left now. We're moving a lot. Okay, some number greater than 3. So now we have a bigger velocity in the negative direction. But at the beginning of 3 seconds, we start getting pulled to the right. Positive acceleration. And so when we have that opposite sign of the two, it's resisting that leftward motion, the negative motion. And so we begin to slow down, but not an immediate stop. We're going to continue moving in the negative direction until we come to a stop. And so 3 to 6 seconds, yes, even the 3 to 4, and then the 4 to 6, okay, all that, show that for a second. Those segments, 3 to 4, 4 to 6, all have that slowdown in the negative direction. So I haven't done math yet because if you notice, we already addressed that yellow cancels yellow. But notice your 0 to 2 seconds, red rectangle, and 4 to 6 rectangle, they both have the same base and height, except one's negative, one's positive. And so what that means is that the change in velocity, the area, remember, between 0 and 3 seconds is a negative something. It cancels the change in velocity, or so I'm going to say negative area and positive area between 3 to 6 seconds. And so I don't need to calculate those. I know they're going to end up canceling out. And so now what happens at 6 seconds? Once you recognize the symmetry, what does that mean? Does that mean we come to a stop? No, not automatically. It means we sped up and then slowed down the same amount. We return to that initial velocity. And so at 6 seconds, we return to a -3 meters per second. Okay? If we had started at rest, then we would come to rest again, but we started with an initial velocity. And so we still haven't come to a stop. We got to keep going to answer the question, do we ever change direction? Remember, we need a 0 velocity and then a sign change of some kind. So we've only been going in the negative direction and we haven't come to a stop yet. So let's keep going. And so let's look at 6 to 7 seconds. So we're a little bit more to the left, right? 6 to 7 seconds. And we have a negative velocity of -3 meters per second. And we still have a positive acceleration pulling on us. And so now we're going to do some math, okay? Because this small area here, okay, slide over. So this area from 6 to 7 seconds, it's a little rectangle, has a base of 1 and a height of +3. So that change in velocity is a +3 meters per second. Now, that doesn't mean much to you maybe until we apply it to initial and final. And so, change in velocity, once again, final minus initial. And I'm starting at 6 seconds, going to 7. And so, if I have a change of +3, and I don't know the final velocity at 7, minus the, remember we return to the given, -3. And so minus a negative makes it a +3, but then I got to subtract it from both sides to isolate V7. And so there you'll notice that the velocity at the end of 7 seconds is equal to 0. Now maybe we just came to a stop sign or the drive-through. How do we know we changed direction? Well, you look at the past and you look at the future. And so here, 0 to 7 seconds, we've been moving in the negative direction. We've been moving in the negative direction. Even 6 to 7, we've been moving in the negative. But at 7 seconds, we come to a split-second stop. Now look in the future. In the future, we've got a positive acceleration and a positive change in velocity. And so since we came to a stop, now the last picture, okay, so we're maybe on our most left, we have a split-second velocity equal to 0. We're going to have a positive acceleration. Yes, it's not constant. So again, think of that rope. You start out pulling a lot, and then it's slipping out of your hands. And so starting from rest at 7 seconds, now I'm going to speed up in the positive direction. Okay? And so now everything up into 7 is negative direction. Now I'm going to be in the positive direction, which then confirms we have completed both criteria for changing direction. So we know it happens. At what time do we answer? So we'd say yes and 7 seconds. So this isn't just acceleration graphs you can't just look at and know when you change direction. Velocity graphs, yes, but not acceleration. You have to dissect it into parts and see what's going on. Sometimes the pictures help. I like pictures, they help me. I like the shading. I do math as needed. And so that multiple representation may be helpful here in the beginning. And then lastly, it says, what is the velocity at 10 seconds? Remember, we just said that we came to a stop at 7. True story, you can get the total area of the whole entire 10 seconds, but remember, the red and yellows are going to cancel. And we've already done the math of the purple shading. We know that we come to a stop. So actually, this answer, I can do just the area from 7 to 10 seconds. That's the one I don't really know yet. And it's a triangle, so 1/2 base times height. 1/2, it has a base of 3, and it had a height of 3. And so we get half of 9, or a positive 4.5. That's the change. Now we need to relate it to the instantaneous velocity that I'm going to call final at 10, because we don't go any further. And so equals final velocity at 10 minus the initial velocity at 7, which we already found is 0. And so we have our answer. Then the final velocity is equal to 4.5 meters per second. All right, now let's take a look at page 16. This is where we're going to forget about numbers for a little bit, and we're going to do some sketches. So in physics, you can do graphs with numbers, or you can just look at the trends, and you can look at the relationships without numbers, and that's a sketch. So you want to be careful on the AP exam. You know, if you want a straight line, get a ruler or your ID edge. If you want a curved line, make sure that it's curvy, okay, so the grader knows. So on page 16, we've got problems that are actually vertical stacks, okay? You are given position graphs, so we know something about position. And we have these blank velocity and acceleration graphs. So these problems are in vertical stacks. Our job is to sketch in the velocity and acceleration. And so I'm not going to do all these. I do encourage you to go try some of them. The key is on Canvas, but you know, try it for yourself. Use pencil. If you're doing it on notebook paper, don't try and get out rulers and do grid lines. Just give your sketch. And so let's do number 2 together, and then we'll do number 5. So you want to start with the given. What's the story? What do we know about the position? And then how does it relate to velocity? Remember from the video that as you go from position to velocity, you need to do slope. And from velocity to acceleration, you need to do slope. Okay? We're not going to need to on this first one, but to go back up, you would do area. Okay? And we can use area here on this first one to just check ourselves. But on the back side, on page 17, you will have to do area. Consider it. And so here, number 2, what can we say about our displacement, our position? And so notice it starts at a high number relative to what I'll call 0, the origin. Maybe we've got a post-it or something that's our origin, our reference point, and we're starting far from it. And then as time goes on, we're getting closer and closer to it. And so we have a final position and an initial position. Now, final is less than the initial. And so if I think about my displacement, it's final minus initial. We're going to get a negative displacement here. Remember, displacement is that position change. And so we know that somehow I got to have negative displacement in the rest of this story. And then we need to talk about velocity. Well, remember, to go down to a velocity graph, you got to take the slope. And so here's where I would challenge you. Get a ruler. And if you notice, if you can see this ruler, I've got a ruler laying on that diagonal line. It's straight, it's constant. And so if you have a constant slope, then so is your velocity. And there's another way to describe this slope. It's more of a decline. And so that's a negative slope. So is your velocity. So how do you show a constant negative velocity on a velocity graph? Well, negative, it's got to be, negative has got to be below in the 4th quadrant. And constant just means it has a constant reading. And so that would be a constant negative velocity as seen on a velocity graph. And so I'm going to switch colors to do that area check, because we said earlier on the position graph, it's a negative displacement. Well, how do you get displacement from a velocity graph? You do area. And so notice you go from your data line to the axes. So I have a negative area on a velocity graph, and that is your displacement. And so it checks out with what we had seen in the position graph. Switching back to purple. Let's keep it going. To go from velocity to acceleration, we need to do slope. Now, you can put a ruler to it, but hopefully you see that that is a horizontal line. It's a constant velocity. Maybe you know the concept that the slope is equal to 0. And if you're on cruise control, then you have 0 acceleration. So on the acceleration graph, you would just darken in that line. All right, so now let's try a curve. Number 5 is a good curve to do. There's some difference from number 2. And so if we look at our position reading, we start at that origin and we're going to end far away. And so that final minus initial position is going to give us a positive displacement. So I'm not doing slope or area there. If it's a position graph, you can get displacement. And then we need to consider slope. So what is our slope doing? Well, it's not constant. And so in order to figure out what's happening, hopefully you remember in the previous video, you want to do tangent slope. And so I'm going to take this ruler and just touch it the curve at one spot. Oh, I thought it would let me write. Sorry, everybody, about my son who can't keep his mouth shut. So there I have somewhat of a tangent line. Hopefully you get the spirit of it. And then I go towards the end and do it again, and we see that's a different slope. And so what is the slope doing? And so remember, slope is rise over run, okay? And it's really about the rise, the change in y, because that's the numerator. And so notice we start out with a very large rise and we end with a smaller rise. And so what that means is our slope is decreasing. And so that means my velocity is decreasing. In what direction? Well, both of these have more of a positive incline, and so they are both a positive slope and a positive velocity. But again, decreasing in value. And so how do we show that on a velocity graph?
I told you to clean up.
All right, so let's draw this velocity story on a velocity graph. And so because it's a positive velocity, we're going to be in the top quadrant 1 region. And so how do we show a decrease? Well, that means it needs to get closer and approach 0 velocity. So we're going to start high and we're going to come low. Now, how do we connect those dots? Well, lucky for you, this worksheet is based on constant acceleration. Lucky for you and us, everybody, that most of the stuff that we do will be based on constant acceleration. Next week, we'll learn constant acceleration equations. And so to have constant acceleration, that needs to have a constant slope on this velocity graph. And so I'm going to connect the dots with a diagonal. And so constant slope, constant acceleration, and it's a decline, it's also negative. And so I can keep it going and put a constant negative acceleration on the acceleration graph in quadrant 4. So again, slope brings you down the stack. Let's do our check for displacement, for area, sorry. And so on our acceleration graph, notice I have a negative area, which means I have a negative change in velocity. Our velocity should become more negative as time goes on. And if you notice, velocity gets closer to 0, so that is a decrease in velocity. Check. And then area of your velocity graph is above the axis, so that's a positive area. And a positive area on a velocity graph is displacement. And that's actually the very first thing we decided on the position graph. So it works out. And so area was just a check for us here. Now the graphs below that I'm going to have y'all try they have some dashed lines. Don't be scared of that. It just means part A, part B. So you can do all of part A and then all of part B. Okay, just be mindful that, when you do part A, you're going to pick up where you left off in part B. And so next, let's go to page 17, where we are given velocity graphs. So here we're given the middle picture. We got to go forward to acceleration, which isn't too bad, but then we have to go back to the position graphs. And so let's take a look at number 3. And so I've got the blue. Let's actually do area first. You don't necessarily have to, but notice from our data line to the axis, I have a shaded area. Yeah, it's a triangle, but it's a negative area, which on a velocity graph tells me that it's a negative displacement. And so a negative displacement, that needs to come up here, that message. So how do we get a negative displacement? Well, in most cases, you want to walk towards your origin. And so we're going to start high and we're going to go low. And there's 3 ways to connect that. We could go diagonal or we could curve. 2 different ways. So how do we know which one is correct? Well, if it was a diagonal, that you have to start thinking about slope, kind of go forward now. If it was a diagonal, that would be a constant slope, which would mean a constant velocity. That's not what our velocity graph says. So we can actually erase that diagonal option. And then each of the other 2 options, they're curves. So they have a changing slope, which is good. We have a changing velocity. So now let's go read the velocity graph so that we can figure out what the slope has to do. The velocity is going away from 0. And so it's getting a bigger number than 0. So the velocity is increasing and it's becoming more negative. So that means it's increasing in the negative direction. And so that on a position graph means that the slope has to do the same thing. The slope needs to increase, it needs to get steeper, the tangent slope, and it needs to be in the negative direction, like a decline. So which one gets steeper? Well, whenever you do a couple of tangent lines, that top option is the one that shows getting steeper. Okay, so that's what the position graph would look like based on this velocity story. It's saying the same thing, just a different way. And then, so that was using slope in reverse, basically. Now let's do slope to get our acceleration graph. This one should be easier at this point. It's a constant slope on the velocity graph. So constant slope, and it's negative, and so will my acceleration. So constant and negative acceleration right there. And so there's some velocity graphs for you to go reverse and get your position graph sketches. And then down at the bottom, once again, you see the part A, part B. So it's not like you have to sit down and do all of these graphs. Usually after a few, you start picking up and you start working faster. But, you know, of the, I don't know, 12 that remain, you know, try 3. And then if you have time, do 3 more. And then maybe another night, do 3 more and 3 more. So break it up. That way you think about physics regularly and you practice it regularly.